All right, good morning again. I hope that everybody is ready to move on. So, the other day, we really started talking about our first physics variables, distance and displacement. But before we go over those, I want to review the two big ones. All right, so remember, we always have two different types of quantities in physics. We have scalar quantities, and then we have vector quantities. All right, remember that scalar quantities will only have magnitude, while vector quantities have both magnitude and direction. So whenever we talked about distance and displacement, distance was our scalar quantity, while displacement was our vector quantity. All right, so remember distance, if I ask you what distance something went, we're looking at the entire path that that object took. The displacement is only looking at the initial and final positions. Initial and final positions. All right, those are the only 2 points that displacement cares about. All right, so with today's two different variables, we are going to be talking about speed and velocity and what makes them similar, what makes them different. All right, now, whenever we talk about speed and velocity, you'll see on this next slide that speed and velocity are both a rate. So we've already talked about this. We know that if we have a rate, we are timing something. So if we have time as a variable, can we ever have a negative time? Can we ever have time going to the left or south or anything like that? No. All right, so what we need to realize is that time is also going to be a scalar quantity. Time will never, ever, ever have a direction for it. All right, so let's get into the difference between speed and velocity today. All right, so speed, first of all, is going to be a scalar quantity. So speed, S, scalar, S. That's the easiest way to remember it. All right, so speed is our very next scalar quantity. I was about to say very first. All right, no, it's our next scalar quantity, which means that velocity is going to be our vector quantity. So again, V for velocity, V for vector. Easy, easy, easy. So with speed, speed is just the rate at which an object is moving. It does not care about the direction that it's moving. It doesn't care if it's going in circles. All right, it's just the rate at which it is moving. So whenever we have speed, because speed is scalar, we are going to use distance, which is also scalar. So we have seen this before. We know that speed is equal to distance over time. All right, so speed and distance go hand in hand. All right, so if I have this car, if we're looking at this car drives this 100 meters in 5 seconds. I want to know what the car's average speed is. All right, so we know that speed is distance over time. Our distance was 100 meters. Our time was 5 seconds. So we know that 100 divided by 5 gives us 20. And we always need our unit, and that's going to be meters per second. So over that 5 seconds, that car went an average speed of 20 meters per second. Now, whenever we talk about average speed and average velocity, that's what you see right here. We'll talk about it more right here, all right, in our next slide. But just go with me. So this is going to be our average speed of 20 meters per second. And whenever we refer to velocity, 9 times out of 10, we are talking about the average velocity of an object. All right, so the velocity, again, velocity is vector. It's our vector quantity, which means that we do take direction into account. Velocity is the total displacement. So we know that displacement is a change in position divided by the total amount of time during the displacement. So in this space right here, I want you to reword that. I want you to say it is our change in position over time. It's our change in position over a certain amount of time. All right, now we know that a change in anything is symbolized by delta. And then we know from our last set of notes that position can either be symbolized with an X or a Y, given if we're moving horizontally or vertically. And anything, delta anything, can be broken down into final minus initial. So we need to remember that little part. All right, over time, that means that we have a rate over time, our time interval. All right, so what I want you to do here, it's weird right here. Let's just X that out, okay? Let's just rewrite it down here. So what that is saying is that velocity or average velocity, so you'll see it either as V or V sub AVG, so that's average velocity, is equal to that change in position, that delta X, our displacement, over our time interval. Now, this is the most basic one. This is the equation that you will be given on your quiz and on your test. You have to remember that anything, delta anything, can be broken down into final minus initial. So this could also be our final position minus our initial position over our entire time interval. If I give you, like I did on the slide before, that it happened in 5 seconds. Well, that 5 seconds is our entire time interval. So that would be our entire delta t. Or I could have, So I could have our final minus initial positions over, say I give you multiple times, all right? That would be our final time minus our initial time. Or I could give you the total displacement and give you the final and initial times. All right, all 4 of these equations mean the exact same thing. But this one right here is going to be the one that we use more than anything. Okay, so we know that our velocity is our change in position over time. All right, now, again, we mentioned this earlier. Why do we call it our average velocity? All right, so say you were coming to school. So you left your house and you traveled 20 miles in 2 minutes. All right, that would be really fast. Just go with me on this. All right, so in 2 minutes. So that would be 10 miles per minute. So you made it here 10 miles per minute. All right, that would be your average velocity. Well, that does not mean that you went that 10 miles per minute the entire way here. No, you probably slowed down to let a turtle cross the road, or you stopped at a red light, or you had to slow down behind somebody who was going slow. All right, so it does not mean that you traveled that speed the entire time. It just takes the entire distance that you traveled, the entire position that you changed, all right, not your whole path necessarily unless it's a straight line path, all right, over your entire time interval. All right, then you divide those and it gives you that average. All right, so it's not necessarily you're not going that speed the entire time. That's just your average. All right, now I want you to put big, huge stars, highlight. We want to make this big. We want to remember this. Velocity and speed are not the same. They are not the same. Now, just like whenever we were talking the other day, whichever one, about how displacement and distance can have the same numerical value. As soon as you change direction, then it's not going to be the same numerical value. And it's the same thing with velocity and speed. If you are going in a straight line and you're not changing direction, then yeah, your numerical values for speed and velocity are going to be the same. You'll just put a direction with the velocity. But if you change direction even the slightest bit, then they will not be the same anymore. All right, so velocity has to have that direction. And if it is a straight line in a straight line motion with no change in direction, then your speed just refers to the numerical value of your velocity. All right, but what if we just look down at our speedometer? Okay, so if we are driving and we look down at our speedometer, what are we looking at? Well, it's the speed. If we're not changing direction at that moment, it could also be our velocity, but it's not going to be our average speed or our average velocity. It's going to be our instantaneous speed or our instantaneous velocity if we were to add a direction to it. All right, that is the speed that we are going at that exact moment. All right, so average speed and average velocity. This is looking at the differences between the two. All right, so let's say, I don't like this. We're going to mark this out. Don't look at this just yet. Go away, go away, go away, go away. All right, so we can see. Enough. All right, so say we walk 4 meters east, 2 meters south, 4 meters west, and finally 2 meters north. So the diagram below is showing you that, which means that this right here is my initial position. So I start off, I go 4 meters to the east, 2 meters south, 4 meters to the west, and then 2 meters north. All right, so the entire motion takes 24 seconds. I want to figure out what the average speed is and then what the average velocity is. All right, so let's take speed first. Okay, so let's do speed over here. So we know that speed is equal to distance over time. Remember, distance is our scalar quantity, so it is taking into account every single motion that we made. So we would find our distance first by adding up all of our motions. So we would add 4 plus 2 plus 4 plus 2, which does give us 12 meters. And we were told that all of this took place in 24 seconds. So if I wanted to know my speed, I would divide those out, and that would give me 0.5 meters per second. 0.5 meters per second. So that is my average speed. Now, my average velocity is my change in position over my time. My change in position is my displacement. Displacement and change in position are the same thing. So I have to first find my displacement. Well, if you look down here, what do we notice about our initial and our final positions? What are they? Hopefully you're saying they are the exact same point. So if I end where I started, then my displacement will always be 0. So my displacement is 0 meters. My time interval is still 24 seconds, but 0 divided by anything is going to be 0. All right, so my average velocity is 0 because I had no displacement. I ended where I started. So once again, you see speed and velocity are two different things, two different numerical values because I changed directions. All right, so now let's go back. Let's revisit our sweet little ant friend from the other day. All right, so whenever we have this sweet little ant, so we talked about his distance the other day. So he went 5 to the right and then went 2 to the left. So his distance was 7 centimeters, but his displacement only took into account his initial position and his final position. So we said that his displacement was only that plus 3 centimeters, plus 3 centimeters. So his initial position and his final position. All right, so his final, if we need a recap, his final position was plus 3. His initial position was 0. So plus 3 minus 0 does give us plus 3. All right, now we are told now that he does this in, this should be, blessed, this should be 5 seconds. There should be a 5 seconds right there. All right, so if I'm trying to find my speed, then I'm going to use my distance. So my speed is distance over time, which gives us 7 centimeters over 5 seconds. Well, 7 divided by 5 does give us 1.4 centimeters per second. So the ant had an average speed of 1.4 centimeters per second. Now with velocity, we're taking our displacement and dividing it by that time interval. So we have that positive 3 centimeters divided by the time interval of 5 seconds. So 3 divided by 5 does give us 0.6 centimeters per second, but we cannot forget about that direction. The direction of the displacement will be the same direction as the velocity, and that tells us that it's moving in that positive direction. Okay, so there is a difference between your speed and your velocity. One takes distance into account, one takes displacement into account. Okay, all right, so let's keep going. All right, so in this example, we have a crow flies east in a straight line. It begins flying at 3.04 minutes and comes to rest at 3.11 minutes. It was flying at an average velocity of 1.5 meters per second. How far did the crow move from its original position or its initial position in meters? Okay, so this is our first real word problem for physics so far. So remember last year, just like in chemistry, we have to use our guess method. So remember our guess method, GUESS. What's the first thing that we write down? Our givens. Okay, so it says that we begin flying, or the crow begins flying at 3.04 minutes. So if it begins flying, that's going to be our initial time. So T initial is 3.04 minutes. It comes to rest, so that's going to be our final time at 3.11 minutes. If it was flying at an average velocity, there's our average velocity of 1.5 meters per second. Okay, those are our 3 givens. Now we write our unknown. How far did the crow move from its original position or its initial position? So we are looking for our total displacement. Now, what I want you to see here, the big thing that I want you to see is that we want it in meters. So we do have meters right there. But what's wrong with our times? Our velocity is in meters per second while our times are in minutes. Now we can do one of two things. We can turn each of these individually into seconds, or we can go ahead and figure out what our delta t is. Remember, delta t can be found by taking t final minus t initial, which means that is 3.11 minus 3.04, which gives us 0.07. All right, 0.07 minutes. So you can either do 2 steps up here or subtract right here and then just do 1 conversion down here. Either way, you're going to get the same thing. All right, so I did the second one. So I did the, no, why did I do that? I did not convert these first. That's what I was trying to say. All right, so I converted them just once down here. So 0.07 minutes actually turns into 4.2 seconds. So now I have my time, now I have my velocity, and I'm looking for delta x. All right, so now our E, if we go back to our guess method, is writing out our equation. So we know that average velocity is equal to our displacement over our time interval. I am looking for my displacement, so I have to get it by itself. I have to isolate our displacement. I do that by multiplying delta t on both sides. So I know my displacement is equal to my average velocity times my time interval. So now I can plug those in. I can substitute in those numbers. So my velocity was 1.5. And just a big note here, I did not give you the specific direction that this crow was flying. So if I don't give you a specific direction, you assume that it's going in the positive direction. So we have a positive 1.5 meters per second times our time interval, which was 4.2 seconds. All right, I want you to see here we have seconds on bottom, seconds on top, so they will cancel out. We multiply those to get 6.3 meters. Now, displacement is a vector quantity, so I have to add that direction to it. So I'll just add that plus at the very beginning. So my displacement was plus 6.3 meters. So this crow flew 6.3 meters in the positive direction in that time interval, going an average velocity of 1.5 meters per second. Okay, now this one is the fun one. All right, I want you to put a star around this one. All right, this one's going to be fun. So it says use the base velocity equation to derive an equation to solve for the final displacement of an object or the final position of an object. Okay, so if we start off with the original, the basic velocity equation, so velocity is equal to delta x over delta t. I want you to rearrange this equation to solve for the final position. All right, well, the first thing that we should notice is we don't have x sub f on this specific equation. So what do we have to do? We have to break down delta x. All right, so we know that velocity can be broken down or equals the breakdown x final minus x initial over delta t. All right, so now we have x final. Now we can begin to isolate it. Well, the first thing that we're going to need to get rid of is that delta t. It's on the denominator, so we multiply both sides by it. All right, so that gives us our final minus initial is equal to velocity times delta t. Well, still trying to get our final position by itself. So our initial position is being subtracted. So if I want to get rid of it, I'm going to add it on both sides. So my final position, if I'm solving for final position, that's equal to my velocity times delta t plus my initial position. All right, and if you look around the classroom and find our kinematics equations, you should see something that looks a little like that. All right, so now we get to our graphs. So we have been looking at distance versus time graphs, displacement versus time graphs, and position versus time graphs. So they're all the same thing. Every single graph that is hanging up in my room right now can be considered any of those three: distance, displacement, or a position versus time graph. All right, so now we should know that if we are trying to figure out the slope of a position versus time graph, we know that that slope is velocity. We are no longer going to say that the slope of a distance versus time graph is speed, because now we can figure out the direction it is going. Positive slope means it's going in the positive direction. Negative slope means it's going in the negative direction. So we'll look at that. So the slope of a line for a position versus time graph, a distance versus time graph, or a displacement versus time graph will always be velocity, no longer speed, always velocity. All right, so let's look at this. I want you to really pay attention to this. All right, so we have a position versus time graph. Let's look at object 1. All right, if I do not have any slope whatsoever, I have a horizontal line, which means I have no slope. That means that I am not changing my position over time. So if I have no slope, that means that I have no motion. No motion. I'm standing still. I am not moving. All right, if I look at object 2, all right, we've already seen this. Object 2 is moving. We have a straight diagonal line. That means we have constant motion. So we have a constant velocity. But we also have a positive slope. That positive slope means that we're going in the positive direction. So we can tell just from this red line that we have a positive constant velocity, or vice versa, a constant positive velocity. But look at object 3. We have that downward slope. It is a straight diagonal line. So yet again, we have another constant velocity because it's a straight diagonal line. But this one has a negative slope, which means I'm going in the negative direction. So for me to interpret this, that means that I have a constant negative velocity. Constant negative velocity, meaning I'm going in the negative direction at a constant speed. Okay, so we're going to do some work on this, do some practice on this, but if you have any questions, then let me know. I'm always here to help.